Hello everyone, I hope you are doing great. In this tutorial video, I want to talk about high intensity focused ultrasound therapy with Comsol multiphysics tools. I hope you subscribe to my channel and share my channel to your friends and leave your comments. Let us start. The high-intensity focused ultrasound is used in many different biomedical applications. These are such as thermal ablation of tumors, transcranial HIFU surgery, shockwave, lithotripsy, and so on. Here, we want to focus on HIFU. The HIFU is a signal that is focused on a small focal zone where its intensity reaches higher levels. In this case, the nonlinear effects may become significant, and one speaks of the propagation of finite amplitude sound waves. The nonlinear nature of the phenomena results in the energy transfer from lower to higher harmonics. The contribution of higher order harmonics grows with the propagation distance. In this example, that is based on a good reference, I modeled the nonlinear propagation of HIFU through a dissipative media using a nonlinear pressure acoustic and time explicit physics interface. These interfaces solve the system of nonlinear acoustic equations in the form of a hyperbolic conservation law, as you can see in reference, using the discontinuous Galerkin finite element method and explicit time integration scheme. The used approach is suitable when the cumulative nonlinear effect, those cumulated through propagation, dominate the local nonlinear effect. Here, the emitted signal is a tuned burst pulse that occupies only a limited part of the computational domain on its way. Adaptive mesh refinement is used for automatic remeshing following the signal propagation. This ensures that the mesh is fine enough to resolve the higher order harmonics where it is required. Okay, before starting the simulation, I provide some application of HIFU. For example, prostate cancer treatment. Here you can see a HIFU probe that is inserted to the body, and the HIFU signal reached to the prostate tumor region, and the treatment will be done. You can see the HIFU probe also here with different schematic, and in the real situation also you can see the related devices. Also, for liver cancer, the patient will put on the MRI scheme devices, and the probe will arrive to the liver region and also inserted to the tumor region, and the ultrasound waves arrive to the tumor region, and the tumor will ablated and will cook. That is when the treatment will complete. And then here also you can see the device that is put it on to the liver tissue with the HIFU device, and then by by turning on the HIFU signals and ultrasound waves, the treatment will be completed. And here also the breast cancer treatment via the same device, but here we have a box that is contained a water tank, and the patient will put in this crack that the breast will treatment with the HIFU signals that coming from the water tank. Okay, here we have a schematic. We have a schematic of water and tissue. It means you can use for liver cancer, breast cancer, or thyroid cancer. And here we have a focal zone that maybe our tumor tissue was inserted and was in here. The focusing of an ultrasonic signal is typically achieved either by using a phase delay or a focusing lens on the transducer side. In this model, a spherically focused ultrasound transducer with a concave lens is used to emit the signal. The transducer housing and the lens are assumed to be rigid. The model setup is shown in this figure, and it is axially symmetric, and the spherical lens of radius r and the aperture A and radius r emits a signal that is a focus at the focal point F. Here the signals are focused in the tissue phantom. The signal is a 5-cycle tune burst with the amplitude P0 that can be tuned. Here we use, for example, 0.1 megapascal, and the center frequency of F0 is equal to 1 megahertz, as you can see here. And the signal amplitude at the source location is enough to generate of higher order harmonics, but not high enough for the formation of shocks, and therefore no special shock capturing techniques are required in this model. The traveling time of the signal to the focal point can be computed as TF is equal to d water divided by c water plus d tissue divided by c tissue. That when we want to add the tumor, it will be modified to a new equation that has a new term plus d tumor divided by c tumor. Okay, here C and D are the speed of sound and the traveling distance in the corresponding material respectively. At the frequency of 1 megahertz, the time to focus is approximately equal to 40 divided by F0. And you can see the source signal in this picture that we can define in Comsol. Okay, let us start. Here I use Comsol 6.2 for the simulation. At first, I add the parameters. Here I provide the parameters in the specific folder. Okay, you can see the parameters. P0, it means source pressure amplitude. F0, it's equal to 1 megahertz. It is source frequency. Omega 0, it's mean source angular frequency. T0, it's equal 1 divided by F0. Absorption coefficient for different material. Here for water at 1 megahertz. As you know, the absorption coefficient it is different for the different wavelengths and also different frequencies. Here we choose 1 megahertz as the input frequency is 1 megahertz. Okay, the alpha tissue, also absorption coefficient for tissue phantom, and the speed of sound in water and tissue with the seawater and sea tissue are available here, and the density of water and tissue, the parameter of non-linearity of water that we can talk about in the following, and the delta water and delta tissue, the diffusivity of water and tissue respectively, and the focal length is 60 millimeter here. The R source and W source are inputted here, and the other parameters. At first, I add a component. I use a 2D axisymmetric. In the geometry, I choose a length unit of millimeter, and I left the other settings. I click right on the geometry and I choose the circle. In the circle, the radius, I type the radius, the R source, yes, and the sector angle 360 degree, and the base is center for 0 and R source. Okay, then I build selected and I choose zoom extent. Okay, then I click right on geometry 1 and I choose a rectangle. In rectangle, in the width section, I type the W source, and in height I type the R source minus SQRT R source squared minus W source squared. Okay, and the base is corner, and I choose build selected. Okay, and I add the intersection here by click right and go to booleans and partitions, intersection. I choose two circle 1 and rectangle, that is synonym by C1 and R1. You can see C1 and R1. I tick the keep interior boundaries, and I build all objects. Okay. I add another rectangle, and in the new rectangle I type the width as R model plus TH ABS, and in height I type the H model plus TH abs minus Z tissue. Okay, and in the position I choose a corner, and Z is Z tissue. Okay, I choose a layers. I type the TH abs. Yes, and I tick the layers to the right and layers on top, and I build selected. Okay, in geometry I add another rectangle. I write the R model plus TH ABS Z tissue minus R source minus SQRT R source squared minus and we must check the excuse me, it must be squared. Okay, and in the position I choose R0 and Z R source minus SQRT R source plus R squared minus W source squared. And in the layer, I take the layers to the right, and in the layer 1 I write THABS. It means it cut the layer from the right with the thickness of the TABs, and the left will be the width of our model. Okay. Now I add the form union. I click right on the geometry. I go to virtual operation. I choose the ignore edge. And I choose the H3 and I build out. Okay. I go to the physics. I add the physics. I search the nonlinear pressure. And also in acoustic we can find it. Here we have many ultrasound pressure physics, but we use ultrasound, nonlinear pressure acoustic. I double click on it, and then you can see the nonlinear pressure acoustic time explicit, NATE, that is the operator for following process. I click right on it. I choose a group by space dimension. I choose all domains. Here I recheck the equation and others, but before checking the equation it's better add the study. I add the time dependent study. I go to a study, add a study, and I choose the time dependent. In the last, I will rechange the time, but at first I want to check the equation with the study of time dependent. As can be seen, the related equation are appeared here. I leave the parameters as a default. In nonlinear pressure, I click right on it and I choose a compute minimum and maximum pressure. Okay, and I choose this line for computing the maximum and minimum pressure. Okay. In the boundary condition, I add the material discontinuity. In interior condition, I add material discontinuity. In this region, it means you separate the water with the tissue. You must see it by rotating this picture. We have the discontinuity here, and I add the pressure, which means the pulse pressure that as input parameter. I add P0 multiplied by pulse T, and I define the pulse T here by, in the global definition, I add the function rectangle from 0 to 5T0, from 0 to 1, and smoothing, not smoothing that, and I plot it. Okay, I add the function, analytic function, with the name of pulse, and the formula of sine omega 0 multiplied to T one minus omega minus cosinus of omega 0 T divided by 5 rect 1 T. Let me check the T. It's not defined here, but we must rename the argument T, x to T. Here I choose automatic derivatives and no periodic extension, and T, the unit is second, and it can be varied from 0 to 9T0. Okay. I continue the boundary condition. In the pressure, I add the displace. That means the pressure will ride from this region to the water and tissue. Now I add the impedance in the boundary condition with the related default equation, and I add these boundaries and I recheck pressure here, discontinuity. Oh, excuse me, I forgot to add this. Impedance, I add these, and pressure here, and material discontinuity, and sound hard boundary must be here, yes, and the axial symmetry here. It's okay. Also, I can add some domain point probe for the evaluating, but before adding them, I go to material. I add the two blank material by right click and blank material. I rename it as the water. Okay. In water, I type the RHO water, and the speed of sound C water, and the nonlinearity of parameter BA water. And I remove these regions, and I add just the region 1 and 4. I add another blank material and I rename it as tissue. And I click on them. I add the density of that as RHO of tissue. And a speed of sound of C tissue. And BA tissue. Okay. In definition, I can add some probe. I right click on them and I go to probe. I add domain point probe. In domain point probe, I choose point probe. Excuse me. I add the point. Let me delete this. Okay, at first I divide this value to P0 to normalize it, and it will be available in the output table. I add another domain point probe. And also I add this point for here. I type the Z as the tissue. Yeah, and you can see the tissue here. Okay, and for second domain point probe, I add the R0 and Z equal to F, which means the focal length. with the same equation divided by P0, and I add artificial domain by absorbing layer, and I add this region by the default equation. Okay, now I go to the mesh and I add the mesh, and also I can recheck the default values of the temperature and absolute pressure here. Let me check that. Here the pressure is 1 atmosphere and the temperature is 293, and the other parameters are taken from the material, and the fluid model I choose the general dissipation, and also then I go back to the material property to add delta diff that equal to delta water, yeah, and for tissue also I add delta tissue. Okay. I go to mesh 1 and also I can recheck another time to see what the okay, here material discontinuity impedance and the data is okay. Here also you can see the variable parameter that will be solved. In the mesh 1 I can add a different mesh I add the free triangular mesh I add 2 sides in size 1 I add the domain, the water domain, and I add the maximum element size in the costume element size as seawater divided by F0 divided by 1.5, and in size 2 I add the mesh of tissue in custom values of maximum element size, I add the C tissue divided by F0 divided by 1.5, and I build all. Okay, and I add 10 meshes here from the mesh. I add mesh, and also I can link with the study. Let me add it for you. And here for the output time, I choose range 0 to with the step size of T0 to 55 T0. Okay. In adaptation, I choose adaptive mesh refinement. I choose manual and general modifications. Then I link the mesh as adaptive, and it will be done automatically. Okay, and in time domain, I click the compute to see what the results. Okay, let me check the absorbing layer. We have an error here. That we must recheck the. Okay, tissue. Water, yes. Pressure, yes. Impedance. Let me compute again. Could not find a spherical region. Oh, in absorbing, I forgot to choose the cylindrical type of the absorbing layer. It's good when you see some error, you can find the related synonyms, and in AB1 we forgot and to change it to cylindrical. Okay, let me recalculate again. Okay, here you can see the probe plot, convergence plot, and it will take about, it depends on your system, it will take 1 hour or 2 hours to run. Running, you can see the results. For example, acoustic pressure, Nate. You can type this equation or any related equation from the nonlinear pressure acoustic. You can see the pressure of total acoustic pressure by Nate.pt. Here I choose the related study. Let me show you. For example, refinement mesh, I can add the different times, for example 0 second. You can see there is no total acoustic pressure, but for example in 33 microsecond, you can see the acoustic pressure was arrived here, and in 55 the acoustic pressure was enhanced and arrived to the higher region. And also in plane acoustic pressure, this is acoustic velocity amplitude, that you can see the velocity of acoustic waves that can change with the time, and you can see in different time it will be different. For understanding, for example, acoustic pressure, let me show you 0 and the 55 microsecond. The evolution of the signal traveling from the source, you can see here that the tune burst pulse has left the source at t is equal to 10 microsecond. You can see here, and travels toward the boundary between the water and tissue phantom, which it passes at t 20 microsecond. It's 20 microsecond, with the some part being reflected back to the source. You can see some of part reflected to source. The focusing of the signal become visible at t 30 microsecond. Here, and reach it maximum at 40 microsecond. You know, it's 1.5 10 to the power of 7 Pascal. And here you can see the relative pressure that we added from the point probe. Here we have the signal at the water tissue interface, that at the focal point, the acoustic pressure amplitude at the focal point is about 10 times greater than the water tissue interface. You can see here and here. And another observation is that the positive pressure peaks are almost twice as high as the negative ones at the focal point. This indicates that the signal becomes highly nonlinear as it reaches the focal zone. Okay. And for this figure, you can see in innate PT divided by P1. Here I add derived values. You can see NET PT divided by P0 in domain point probe 1 in all time by just adding point probe expression by point evaluation. I add them, and you can see the both equation for domain point probe 2 that is here from 0 to F domain point probe, and the first is here. Okay. For understanding this this figure, it's frequency spectrum of the acoustic pressure at the water tissue interface and at the focal point. This fig shows the frequency content of the recorded signal. That frequency content of the signal entering the tissue phantom that is not much different from the source signal. It is propagation up to this point that is linear. The signal at the focal point is, however, highly nonlinear, which is seen from the number of generated higher order harmonics. Okay. And for this figure, you can see innate P maximum at 81.0F innate P maximum, that the data is was given from the refined mesh solution component spatial RPZ from 0 to 1. And for understanding this figure, let me the plots of minimum and maximum on axis pressure calculated are shown here. The values are computed according to the equation of P minus equal to minimum T related to 0 to Tn, and P plus is equal to maximum T related to 0 to Tn, that are normalized with the respect to maximum pressure at the focal point, and P plus is almost twice as high as P minus, you can see, which is distinctive feature of nonlinear propagation of a HIFU signal. The bounds of the focal zone are also seen in Fig 6, that is here, this figure. Okay, also here I provide a cell wave time scale with the innate WTC. Also you can add the cell time scale, acoustic fields, acceleration and velocities. There are many data that you can export from the results. For example, here in intensity, magnitude, and you can plot it. You know, there are many data you can export. Okay, here also you can add a tumor. For example, here we have a tissue. I can add, for example, a circle, and I rename it as a tumor. And I can bring it here. Here we are 60 millimeter, and here 30. Let me 30, 60. Okay, and I can change it as a R tumor. Okay, Control C. and here I can add it, for example 5 millimeter. Then you can see a tumor here, for example, and you can add a material, a blank material, and add it as a tumor. Here the tumor, it can be for example prostate tumor, breast tumor, liver tumor, or something else. You can rename it, for example liver. You can add density, speed of sound, and you must find them from the paper, and you can do it as an exercise by yourself. Okay, I hope you enjoyed this video. Please subscribe to my channel, share my channel to your friends. Please leave your comments, like my videos, and support me. And you can help me by bringing project for me and grow my community. Thank you very much. Have a good time. Take care. Goodbye.